causal machine learning for healthcare and precision medicine.
Yeah.
Okay.
So can I start? No?
Yes, please start.
Yeah, okay, thank you very much. Yeah, actually today I am going to talk about a paper titled Causal Machine Learning for Healthcare and Precision Medicine. This is a very basic paper in for causal model, and mainly it is descriptive. Actually, I try to find some differences between causal model and generalized machine learning model. Generally, in machine learning model, in order to improve performance of a model, we use transfer learning. That means when a model fail on a new data set or reduce performance on a new data set, generally we mix or rearrange training and validation data set to improve the performance or to improve the generalization ability. From this point of interest, I try to understand this paper, and which I am going to present now what I read from here. So you know that causal machine learning has experienced increasing popularity in healthcare. It provides a complete tool set for investigating how a system would react to an intervention. As for example, outcome for a given treatment. So quantifying the effects of interventions allow us to be made actionable decisions in the presence of confounders. This paper basically explored how causal inference can be incorporated into different aspects of clinical decision support systems. It used Alzheimer disease as an example to create illustrating advantageous points in clinical scenario using causal machine learning model. It's also discussed some important challenges present in healthcare applications for high dimensional and unstructured data, and also the generalization ability in different environments, or generalization ability for out of distribution data, and for the temporal relationships from the time domain data. It also reviews some papers which offer the potential toward addressing those challenges. So in considerable progress has been made in predictive systems for healthcare following the advent of powerful machine learning approaches such as deep learning. In healthcare, clinical decision support tools make prediction for tasks such as detection, classification, and or segmentation from electronic health record data such as medical images, clinical free text notes, blood test, and genetic data. So those systems are usually trained with supervised learning techniques. However, most CDS systems powered by machine learning techniques learn only associations between variables in the data without distinguishing between causal relationships and correlations. Even with the appropriate data and perfect performance, current machine learning system would predict the best treatment based only on previous correlations in the data, which may not represent actionable information. Such systems need causal inference in order to make actionable and individualized treatment effect predictions, which is the main expectation or main goal of our clinical decision support system. So a major challenge in healthcare is how to capture the necessary information to causally reason about treatments and outcomes. Modern healthcare data are multimodal and high dimensional and often unstructured. So information from medical images, genomics, clinical assessments, and demographics must be taken into account when making predictions. A multimodal approach better reproduce how human experts use information to make prediction. In addition, many diseases are progressive over time. So our system must, or it is necessary to the temporal dimension, to take the temporal dimension to improve the performance. Finally, any system must ensure that this prediction will be generalizable across deployment environment, such as different hospitals, cities, and countries. Interestingly, it is the connection between the causal inference and machine learning that can help reduce these challenges. So between the causal inference and machine learning, the machine learning permit causal models to process high dimensional and unstructured data by learning complex nonlinear relations between variables. Where CI adds an extra layer of understanding about a system with expert knowledge, which improves information merging from multimodal data, generalization, and explainability of current machine learning system. The causal machine learning literature offers several directions for addressing those challenges when using observational data. This is an hypothetical example that illustrated how the CML directions, which I have mentioned, can be incorporated into healthcare. CML in healthcare help understanding biases and formalizing reasoning about the effect of interventions. With this hypothetical example, the authors illustrated that high-level features can be extracted from low-level data into a graph corresponding to the data generation process. As for example, here the I1 might correspond to the brain volume derived from a medical image. CML can be used to discover which relationships between variables are correlations and which are causal. Here in this figure, the dashed line represent the correlations and the correlation relationships, and the solid line represent the causal relationships. Finally, the CML offers tools for reasoning about the effect of intervention. Here we shown the do operator. For instance, an intervention on D1 would only affect the downstream variable in the graph, while the other relationships are either not relevant due to the graph mutilation or remain unchanged. In practice, predicting a disease with almost perfect accuracy for a given patient is not what precision medicine is trying to achieve. Rather, their goal is to build machine learning methods which extract actionable information from observational patient data in order to make interventional decisions. In order to make actionable decision at the patient level, one needs to estimate the treatment effect, and the treatment effect is the difference between factual outcome and the counterfactual outcome. So for actionable predictions, we need algorithms that learn how to reason about hypothetical scenario in which different action could have been taken, creating therefore a decision boundary that can be navigated in order to improve patient's outcome. When using observational data set, we never observe the counterfactual outcome. Therefore, the best treatment for an individual, which is the main goal of precision medicine, can only be identified with a model that is capable of causal reasoning. That's why it is necessary to consider a causal framework in healthcare as compared to the other methods. So this author introduces two approaches here to build a causal model. So in these slides, actually, at first, they give a definition of the causality. I think everybody know about this one. Generally, the causality means that if A is a cause and B is an effect, then B relies on A for its value. As causal relations are directional, the reverse is not true. So A does not rely on B for its value. The idea of causality thus enables analysis of how a system would respond to an intervention. So the questions such as how will the disease progress or a disease progress if a patient is given treatment X, or would this patient still have experienced outcome Z if treatment Y was received? And such type of questions require methods from causality to understand how an intervention would affect a specific individual. In a clinical environment, causal reasoning can be useful for deciding which treatment will result in the best outcome. So they introduced two approaches of defining and reasoning about causal relationships. One is the structural causal models, and another one is the potential outcomes. The mathematical formalism around the so-called do calculus and the SCMs has allowed a graphical perspective to reasoning with data which heavily relies on domain knowledge. And this formalism can model the data generation process and incorporate assumption about a given problems. So, and the SCM can be defined as this following expression. It's a consist of collection of S of structural assignment called mechanisms, where X of K equal F of K, PA and NK, where PA of K is the set of parent variables of XK, its direct cause, and NK is a noise variable for modeling uncertainty. Where N is also referred to as exogenous noise, it represents variables that were not included in the causal model, as opposed to the endogenous variables X, which are considered known or at least intended by design to be considered, and from which the set of parents P of P, K are drawn from X. This model can be defined as a directed acyclic graph in which the nodes are the variables and the edges are the causal mechanisms. According to the principles of independent causal relation mechanisms, we assume that the causal generative process of a system's variable is composed of autonomous modules that do not inform or influence each other. This means that the variables N are mutually independent with the following joint distribution. And the joint distribution over the endogenous variables X can be factorized as a product of independent conditional mechanism. as illustrated in this figure, after an intervention, the ages between the intervened variable and its parents are not relevant, resulting in a mutilated graph. The causal structure enforces that only the descendant of the variable intervened F1 will be modified by given actions. And then the do calculus introduces the notion do of D1 to denote a system where we have intervened to fix the value of D1. Thus, SCM allow us to the following problems like associative predictions, interventionals, and counterfactual queries. In the potential outcomes, a response variable Y is used to measure the effect of some cause or treatment for a patient's eye. And the value of I may be affected by the treatment assigned to I. To enable the treatment effect to be modeled, we represent the response with two variables. One is the outcome under the treatment conditions, which we call the treated, and the another one is the outcome under the control condition, which also we denoted as untreated. The effect of treatment on a patient eye is then the difference between the response or outcome of the treatment condition and the control conditions, which is expressed by these following expressions. So causal reasoning in the potential outcome framework depends on obtaining an estimate for the joint probability distribution between the outcome of the outcome under the treatment condition and the outcome under the control conditions. So determining the cause of effects requires hypothesis and experimentation where interventions are performed and studied to determine the necessary and sufficient conditions for an effect or disease to occur. Both structural causal model and potential outcomes approaches have useful applications in practice, while graphical SCM are powerful for modeling assumptions or identifying if an intervention is even possible or not. And the potential outcomes literature is more focused on quantifying the effect of interventions.
So, Ibrahim, do they even talk about equivalence of potential outcomes and structural causal models?
You mean the difference, right?
No, well, they're basically doing the same, I think. I think there is a proof that they are equivalent. Okay, so they don't know. They're morphologically look different, but they really doing the same thing. Okay, so they don't talk about it.
So I think the SCM is used for the causal representation or data generation process.
No, it's used for effect as well, causal effect estimation, and potential outcomes is used for causal effect estimation.
I mean, the potential outcome is used to quantify the effect of intervention.
And SCM,
right,
well.
right,
Yeah.
And the SCM is used to identify.
No. Quantify, identify, the same. SCMs assumes the structure is given, so they're both giving you
quantify. It means how much. That means which one is the best.
Both of them answer that question.
Yeah.
Both of them answer that question. How much? How much will Y change if you affect if you do something with B or affect B? Okay. Anyways, so
in this actually from my reading from this paper, they said that suppose if that means how, that means how can I say, if a patient, that means what is the effect of a patient when the treatment X is given? Does it change or not? Using they identify using the SCM.
Well, the amount of change, SCM
they're
does the amount of change.
Okay, but I think they're saying that potential outcome is the amount of change, or same, I don't know.
Both of them can do it.
Okay.
Yeah.
Okay.
Thank you. I'm surprised
Okay.
that they didn't talk about it, but okay.
Okay. So in this paper, they use a example. They use the Alzheimer disease to understand from a causal perspective. So in this case, they use a simpler view with only 3 variables like chronological age and magnetic resonance images of the brain and the AD diagnosis. The diagnosis of AD is made by a clinician who takes into account all available clinical information, including images. And we are particularly interested in MR images because analyzing the relationships of high dimensional data, such as medical images, is a task that can be more easily handled with the ML techniques. From these 3 variables, so here they consider that AD causes the symptom of brain morphology changes, but the chronological age cannot be caused by AD nor any change in brain morphology. So in this scenario, they can assume that the age is a confounder of the brain morphology measured by the MR image and the AD diagnosis. So these relationships are illustrated in the causal graph. This is the left figure. To model the effect of having age as a confounder of brain morphology and AD, they use a conditional generative model from a previous work. They're from their previous work, in which the condition on age and AD diagnosis for brain MRI image generation. So the causal graph left and the illustration of how brain changes in MR images in response to intervention on age or Alzheimer disease status. And the middle image used as a baseline is from a patient age 64 years old who is classified and cognitively normal within the ADNI database. They synthesize images of a patient at different ages while fixing Alzheimer disease status. In particular, they control for one variable where intervening on the other. That is, they synthesize image based on a patient who is cognitively normal for their age of 64 years, then fix the Alzheimer disease status at control and increase the age by 3 years for 3 steps, resulting in images of the same control patient at the ages of 64, 67, 70, and 73. At the same time, they synthesize images with different Alzheimer status by fixing the age at 64 and changing the Alzheimer disease status from mild cognitive impairment to a clinical diagnosis of AD. This example illustrates the effect of confounding bias. By observing qualitatively difference between the baseline and synthesized images, we see that the aging and the AD have and the AD have similar effects on the brain. That is, the both variables changes the volume of brain when intervened on independently. So throughout this paper, they will further add variables and causal links to this example to illustrate how healthcare problems can become more complex and how a causal approach might mitigate some of the main challenges. In particular, they will build on this example by explaining some consequences of causal modeling for dealing with high dimensional and unstructured data, generalization and temporal information. So the AD example illustrates the importance of considering causal relationships in a machine learning scenario. That is, the causality gives the ability to model and identify types and source of bias, to correctly identify which variables to control for, and the causal graphs offer a direct means of visual exploration and consequently explanation. By representing the variables of a particular problem, their causal relationships as a causal graph, one can model with different scenario like domain shift, such as population shift, acquisition shift, annotation shift, or data scarcity. That means the data imbalance. To illustrate the importance of the causal models, they have shown the results of a convolution neural network classifier trained and tested on the ADNI data set for AD classifications. This table illustrate of how a trained classifier, as for example, the neural network, that is the CNN, fails when the data generation process and the causal structure are not identified. They highlight that the group with worse performance is the older cognitively normal patients due to the confounding bias. But after training with the counterfactually augmented data, the classifier precision for the worst performance age group improved. So using the augmented data based on causal knowledge, where the training data are augmented with counterfactual images of a patient when intervening on age, that is, images of a patient at different age while controlling for Alzheimer status are synthesized, so the classifier learn how to differentiate the effect of aging versus Alzheimer disease in brain images. This causal knowledge enables the formulation of best strategies for mitigating data biases and improving generalization. Beside the diagnosis, a major challenge in healthcare is ascertaining whether a given treatment influences an outcome. For a binary treatment decision, for instance, their goal is to estimate the average treatment effect using these expressions, where y of 1 is the outcome given the treatment and y of 0 is the outcome without it. That means it's control, which I have already mentioned in the previous slide. And y I of 1 for a given patient I, this is typically estimated using this expression where t is the treatment assignment. This figure illustrates the difference between individualized and the average treatment effect. The individualized treatment effect for each patient is the difference between actual and the counterfactual outcome, which show that an example that the individualized treatment effect for some patients might differ from the average treatment effect. So the estimation of treatment effect using observational data is subject to confounding as patient characteristics affect both the selection of treatment and outcomes. And here the causal inference method need to mitigate this. Now I'm going to talk about the CML for complex data. Generally, the psychiatric disease has multiple causes arising from complex interactions. A recent attempt to build causal graph for describing Alzheimer's disease takes into account where data derived from several data sources and modalities, including patient demographics and clinical measurements, genetic data, and imaging exams. The several new procedures of measuring biomarkers are increasingly accessible and affordable, but integrating this information is not easy. In addition, performing interventions with complex data representation and function is challenging. And also, many diseases progressive over time. So where the environmental factors over time contribute to different disease trajectories in AD. As for example, poor sleep quality leading to neural dysfunction, which may create positive feedback loop between sleep and AD in the causal graph. It is therefore important to consider data-driven approaches for understanding and modeling the progressions of disease over time. For treatment decisions, causal inference methods need to model patient history and treatment timing. So estimating trajectories under different possible future treatment plans is extremely important. Early work has used temporal causal inference in neuroscience, but the applications of temporal causal inference in combination with the machine learning for understanding and dealing with complex disease remains largely unexplored. The challenges of integrating different modalities and time information increases when unstructured data is used. So the processing of unstructured data is mostly tackled with machine learning, and generalization is one of the biggest challenges here. Here we're interested in realistic setting where the test data distribution might be different from training data distribution, and this setting is often referred to as out of distribution generalization. So from this reference paper, they stated that causal relationships are stable across different environments. In a causal learning, the prediction should be invariant to distribution shift. Imagine a prediction problem where the goal is to learn probability of y given x. We consider an environment variable, ENV, which controls the relationships between y and W, and ENV is a confounder between these two variables, and x is caused by the two variables y and W. Firstly, we consider the view that the most prediction problem are in the anti-causal direction. That is, when making a prediction from a high-dimensional unstructured variable x, as for example, brain image, one is usually interested in extracting and or categorizing one of its true generating factor y. That means, as for example, gray matter volume. So probability of x given y, which represent the causal mechanism and which is independent of probability of y given environment. However, this is not probability of y given x is not as probability of y given x is defined by this expression. Thus, probability y given x changes as the environment changes. Secondly, another genetic factors, W is often correlated with Y, which might cause the predictor to learn the relationship between X and W instead of the probability of Y given X. So we can now describe several ML settings based on the causal perspective by comparing data availability at the train and test time. Therefore, as for example, the classical supervised learning uses the strong assumption that the data from train and test sets are the independent and identically distributed. Therefore, we assign the same environment for both sets. In case for semi-supervised learning is a case where the part of the training samples are not paired to annotations. And another one is the lifelong learning. Consider the case where the data from different environments are added after training. And the challenges here is that to learn new environment without forgetting what has initially been learned. And in domain adaptation, only unpaired data from the test environment is available during training. And for the domain generalizations, learn how to become invariant to the change of environment such that a new environment can be used for the test set. The causal machine learning, we call the CML, literature offers several directions for addressing those challenges when using observational data. Here we categorize CML into three directions: causal representation learning, causal discovery, and causal reasoning. Causal representation learning refers to a compositional view of machine learning. Instead of a mapping between input and output domains, we consider an intermediate representation that captures concept about the world. The idea is essential when considering learning and reasoning with real healthcare data. The idea of causal representation learning is to reinforce the hierarchy of latent variables following the causal model, which in turn should follow the real data generation process. Basically, it learns to extract low-dimensional informative variables and their causal relations. So in causal discovery, it's the task of learning the direction of causal relationships between variables. So we know that the most of the real data are observational, and discovering causal relationship between the variable is more challenging because we have many input variables, and the goal is to construct the graph structure that best describe the data generation process. We cannot consider all of the observational variables during the causal discovery. So let's say given a set of variables, it learns the causal relationships between them. So causal discovery is still an open area of research, and some of the major challenges in discovering causal effect from observational data are the inability to identify all potential sources of bias, select an appropriate functional form for all variables, and also in case for model temporal causal relationships.
Hey, Ibrahim, how many slides do you have left?
Sorry?
How many slides do you have left?
I don't understand. Slide?
We wanted to give May time to give her presentation.
Yeah, just going to finish.
Okay.
Okay. So in causal reasoning, Given a set of variables and their causal relationships, we analyze how a system will react to interventions. So in SCM, counterfactual estimation with deep learning, like generative models such as normalizing flow, variational autoencoder, and diffusion probabilistic model, and twin networks which augment the original SCM, resulting in both factual and counterfactual variables represented simultaneously. And in the potential outcomes framework, a number of approaches have been proposed to estimate personalized treatment effect, which is shown here. So in this paper, they describe the importance of considering CML in healthcare systems, and they also highlighted the need to design systems that take into account the data generation process. A causal perspective on machine learning contributes to the goal of building systems that are not just performing better, but are able to reason about potential effect of intervention at population and individual levels. They also discuss some challenges in precision medicine and healthcare using multimodal, high dimensional, and unstructured data. Okay, thank you. Thank you for your patience. This is my presentation today.
Thank you, Ibrahim.
Yeah.
So for the interest of time, let me stop the recording here and switch to my. We have